Um, Hello everyone, thank you for coming. Sorry for the issues. My name is Martin. I work for Cake Solutions, a software services company working with Scala, big data, distributed systems, enterprise systems, and machine learning as well. Today I'll talk about data in motion, about streaming static data efficiently. I'll focus on Akka Persistence, a specific use case, but I will generalize the use cases to many other areas of software engineering and distributed systems. So just to introduce the topic, traditionally many companies or still are using many different systems communicating randomly with each other, and it's difficult to scale these systems and maintain consistency of the data in the distributed environment. Similarly, many companies are using batch processing, so they take a snapshot of the data at a point in time and run some analytics on transformations on the data. But what they really want to do is to run this pipeline as often as possible or immediately, but they run it every hour or every day, which is not really what they can do. So they can do a bit better. We would really want our data pipelines to be scalable, to be performant, to be elastic, consistent, available, fault-tolerant, and at the same time achieve the production readiness in distributed environment. So maintain all these things in production environment. One way how to handle this is using streams. So streams have multiple publishers and multiple subscribers, and we can define some sort of computational graph. This graph can have joins, can have broadcasts, it can have projections, maps, and other operations. And we can also have the arrows going the other way, so back pressure or acknowledgements for reliable delivery. We usually define this computational graph independently on the execution of the graph, of the materialization. So these are two independent steps. There are many use cases for streaming data, such as sensor data, social network data, Internet of Things, finding patterns in the data, training machine learning models, or using models on streaming data. So today I'll talk about streaming static data. There are essentially two ways or two sources, non-replayable sources that cannot be replayed multiple times. So if we lose the data, we cannot replay the data again, and replayable sources that we can replay multiple times. And we'll talk about these the most today. A good example is a general database. So we have a database with multiple rows. Each row has something like a primary key, and these keys define some sort of ordering between those rows. And we can essentially just read the database row by row and produce a stream of elements, which works very well. We have all the attributes that we want, such as ordering. But what if we add a new element into the database? Now, it is difficult to know which elements were actually added. We would have to remember all elements that we already emitted, or we would have to remember at least a timestamp for each materialization of the stream. So every time we would replay the database, we would need to remember a timestamp of the last emitted event, which can be very, very memory or disk consuming. Also, if we now emitted this new row, we would not have the ordering properties that we had previously. So multiple materializations of the same stream would not be the same. Similarly with updates to database tables. So now the value of 5 changed to 55. And again, we would need to somehow know that this was changed, similarly to previous slide. And also, if we emitted it, we would again, we wouldn't have the properties that we had previously, such as ordering. And we would have two values for the same key, which we ideally do not want. So a mutable table does not represent a stream, but it represents a snapshot of a stream in point in time. Another option, how to get data from a database, is to push data from the database. So there are databases that actually support this, such as MongoDB, PostgreSQL, MySQL, and others. So if a new element is added, the database will immediately push it into the stream. This is usually called change data capture or a change log. A very useful feature, and in combination with the previous one, so we pull the data, we take the consistent snapshot of the data, and then we emit the changes. We can actually reconstruct the same database again from the changes, and it will always be kept up to date with the changes. But there's a simpler option how to emit data from a database, and that's called log data structure. The log is an extremely simple but very, very powerful data structure. We always only append data at the end of the log. We can replay it from the beginning or from an offset. It defines a total order of operations. So every time we replay the same log, it will always have the same ordering. And also, we just need to remember a single number, an offset, that defines where we are in the stream. It's very, very useful for many use cases, and it's used usually where durability is extremely important, such as in databases in write-ahead logs. So we, in a database, when we're performing a transaction, the database usually writes first into this write-ahead log, and if there's a failure, it will reconcile the write-ahead log with the state of the database and make sure it's correct. It's also used in database replication, in distributed consensus algorithms for log replication, and other use cases where durability is very important. So when streaming or when creating a stream from a log data structure, it's much simpler than the previous case, because new element will always be added at the end of the stream or the log. So we just remember the offset of the last one that we emitted, and we simply emit the new one. Another property that this gives us is the ordering. So the ordering is maintained. Multiple materializations of the same log produce exactly the same stream, or the previous one is a prefix of the next one. Right, so let's talk about Akka persistence. I'm assuming most of you are familiar with Akka. It's a actor framework on the JVM. It uses the actor abstraction for isolation, supervision, and asynchronous message passing. But it's mostly useful for building general distributed systems. In this case, we have multiple machines. So we have an Akka cluster or Akka sharding. We can address each actor by its key, by this actor's name, and we can send messages to them. These actors, they have a mutable state, but this state is only in memory. So when the actor receives a message, it can change its mutable state. But if the actor dies, or if the whole machine died, we would lose all, we would use that mutable state. So Akka persistence stores the events, so the changes to the mutable state in a database, in a log. It's essentially a write-ahead log. And if there's a failure, then the actor can replay these messages from the log and reconstruct its mutable state. Similarly with rebalances, so when the actor moves to a different node, it can do the same and reconstruct the state. There's also a component called Akka Persistence Query. And this creates a stream of events from that event source journal, from that log. There are 3 streams supported at the moment: events by persistence ID, which gives us all events for a single particular actor, all persistence IDs, which gives us all names of all actors in the system, and events by tag, which creates a stream of all events that have a particular tag. So most credit for the implementation of this in Akka persistence using Cassandra database goes to Patrick Nordvoll and Martin Krasser, but I had the opportunity to participate on the implementation. So I'll talk about some of the implementation details, design considerations, and I'll explain the decisions and some of the implications, especially generalize that to distributed environment. So there are multiple implementations of Akka persistence. We'll talk about the one for Cassandra database. Cassandra is a distributed, highly scalable and available database. It uses replication and sharding and a wide row data model. If we use the CAP theorem classification, it would lie somewhere in the AP area, so it's available and partition tolerant. One of the main abstractions is called the partition. Partition can have multiple rows. A single partition always lives on a single machine, but a partition can have multiple rows. We will not talk about the rows here. We will just represent them as events. So each event will be a row. But in this case, we're only really interested in the sequence number. So the increasing sequence numbers, event 0, 1, 2, etc. Each partition has a partitioning key, which is essentially a pointer to this partition. In our case, it's a tuple persistence ID partition number. And if we have this pointer, we can find this partition very efficiently. The persistence ID is the name of the actor, and partition number is the number of partitions. So the partition lives on a single physical machine, so it can grow very large. But we want to manage that size of the partition, because if it's too large, it's not very efficient. If it's too small, we need to query more partitions. So that's not efficient as well. So we want to manage that size. So we can, for one actor, we can have multiple partition numbers because we manage the size of the partition. Finding an event in a partition is very efficient. However, going through multiple partitions or scanning multiple partitions can be incredibly inefficient. So we would want to avoid that as much as possible. So we have implemented this generic. Is it readable at all? So we've implemented this generic actor publisher that essentially reads data from the log from a database and produces an akka stream. It defines a couple of methods that the implementing classes have to implement, such as define what the initial state is, how to update the state if a new element is received, and a couple other methods, which might seem quite simple, but it actually requires a lot of asynchronously handling a couple of events. So, for example, it's in akka streams, so the downstream components using backpressure, so they can ask for more data. So it has to keep a buffer of elements and provide new data when the downstream components ask. It has to handle the timeout queries, because at some point it will reach the end of the log and it needs to know when to query the data again. So we keep some sort of timeout and requery the database multiple times after the timeout. It needs to asynchronously get data from the database. It needs to prefetch the data from the same partition or the next partition. It needs to maintain a buffer. So when all this has to be handled fully asynchronously in an asynchronous environment, and it has ideally should never block a thread. So the first implementation is events by persistence ID, which should give us all events for a single persistence ID for a single actor. The database query looks exactly as we would expect a Cassandra query to look like. So we specify both the parts of the partitioning key and a range of sequence numbers. So querying the database like this should be very efficient. So we essentially just go through all events in one single partition or a couple of partitions for that single actor, which should be very, very efficient. And the code is actually very simple as well. The only state we need to remember are essentially 3 numbers. So we need to increase the sequence number, the count, and the partition number. So just 3 numbers, very efficient. All persistence IDs, a query or a stream that should give us all persistence IDs, names of all actors in the system, is a bit more complicated. So the query still looks reasonable. Select distinct persistence ID partition number from the table. But if you think about it, it has to go through all nodes in the cluster, and the tuple, the distinct also specifies the whole tuple. So it will give us this one, so we emit the 0, which is the name of the actor. It will also give us the second tuple, but we have already emitted 0, so we don't want to do it again. And then we can emit 1, which is still fine, but the partitions in Cassandra, they have no ordering between each other. So if a new one is added, we don't know where. So we just need to query the database again, and we need to keep a set of all persistence IDs that were already emitted. We need to compare these 2 sets and only emit the new ones. So that's very inefficient because we're doing streams, and streams are unbounded. So we need to potentially maintain an unbounded a set of persistence IDs that were already emitted. And events by tag is by far the most complicated one because if we wanted to emit all, so firstly, when writing an event, we can assign a tag to this event. So events for a single actor, they are ordered by sequence number, so they have some sort of causal consistency. But events between multiple actors, they have no ordering whatsoever. They're completely independent. But we can assign an event, when writing an event, we can assign it a tag, and it links events together, which is useful for creating some sort of aggregations in between actors. But to be able to query those, we would have to go through all, potentially in parallel, but we would have to go through all partitions in the whole cluster. So we would have to scan all of them and only emit those that have a tag, and we would emit those to the stream, which is incredibly inefficient, and is something that we never want to do in a database, in distributed database like Cassandra. So the way this is usually handled is by restructuring the data in a different way. So we create a materialized view, a different view of the data. The data is differently repartitioned, differently structured on the disk. And then we can easily, quite efficiently, go through the events that are in the view. So that works very well, but there are a few issues. Firstly, it's heavily dependent on Cassandra 3 implementation of materialized views. So we cannot use the different backends, such as Kafka or something else. Also, we don't have much control over the subpartitioning. So we need to use something like a time bucket. It can be a day, it can be a week or a year, but we cannot manage it with more granularity. So in some day, you can have plenty of events with the same tag. Other day, you may have very little of them. So it's not efficient, and after a few years, you will have plenty of partitions. So going through all of them will not be very efficient at all. But the biggest issue really is that Cassandra replicates the data from the original table to the view in parallel, which might not sound like an issue, but we do have some causal consistency between events for a single actor. So they define ordering. And we also have consistency between multiple partitions for the same actor. So we cannot just replicate them in parallel because we would lose the causal consistency. Events that are in later partition may be replicated earlier. So it will eventually be fine, but for a period of time we may lose the causal consistency, the partial consistency, or the monotonically increasing sequence number. Similarly, when writing two events for the single actor, one write can go to one node, another node write can go to a different node, and the later one can be replicated first under certain circumstances. So again, we only have eventual consistency, but we would really want stronger consistency guarantees, which might be an issue using this implementation. The problem is there's no way how to handle this on the read side efficiently. So assume we have emitted ID 0, event 1 for ID 0, that's fine, but the next one is event 100 for ID 0. So we don't know if this is the next one that we should emit into the stream, because there may be others in between them, but we just don't know. The only thing, this can only work, we can manage the increasing sequence number only if all events for an actor are tagged with the same tag. Then we can maintain the sequence number and make sure the causality is there. But in general case, we cannot do it. So the way it is currently handled in Akka Persistence Query is we just delay the reads from the database by a configurable amount of seconds. By default, it's 10 seconds, which unfortunately, you have to wait for the events 10 seconds, which may not be ideal use case, especially for real-time use cases. And at the same time, it's still non-deterministic. So if your cluster, if there's a lot of events in the cluster, or if you have a network partition, the replication may actually take much longer than that. So it's still non-deterministic, and we may not get the correct result. One of the most important features of Akka Persistence Cassandra is replay. So we need to replay all events for a single actor and reconstruct its state. This is the original implementation. Firstly, it just wrapped a blocking call in a future. And secondly, it used this notion of iterators, which used a lot of vars and nulls, which is not really the ideal functional code. On the other hand, it was pretty low level, and it was actually really performant on a single thread. But the biggest issue was this code, this row iterator. So it calls the session.execute, which is a blocking call to a database, which we would ideally want to avoid. And another issue, a bit more hidden one, is that the DataStax Java Cassandra driver does a blocking call to a database and then keeps an internal buffer. And when you call iterator.next, it will give you a next element from the buffer, which works fine. But when you exhaust the buffer, it will actually perform another blocking call to a database, which ideally we would want to avoid. But with Akka Persistence Query implemented, we can actually reuse the actor, the events by persistence ID stream that we saw previously, and we can actually just simply call queries.events by persistence ID, which will give us a stream of all events for a single persistence ID, which is exactly what we need for replay. So the code is much simplified. It's fully asynchronous, non-blocking calls to database. And also, we specify the correct consistency guarantee. So read and write of at least a quorum, we will get the strong consistency that we need for this use case. This new implementation is slower on a single thread. On the other hand, if there are multiple threads available, the performance is actually, in most cases, better than the previous implementation. If you want to tune the implementation, definitely have a look at things like the thread pool assigned to the replay, so the dispatcher available, and also definitely have a look at things like the size of the buffer, size of partitions, and other parameters. So that's the current implementation. But we also, during the design phase, we discussed another possible implementation. And I would like to talk you through this other alternative implementation, because it very nicely explains some of the concepts, how streaming works, and how many concepts work in general distributed environment. So the first component would be essentially a write-ahead lock, a physical stream per node. So when an actor writes a message on a node, it will immediately write it to a physical partition on the same machine. So each of those physical partitions can have events for multiple actors, and because an actor can move between nodes, actors' events can live in multiple partitions. Because Cassandra gives us atomicity and isolation when writing to a single partition, it's a good start for the consistency guarantees that we will later need. Then we will merge all these physical streams into one single all events stream. We define an order of these events, and the only thing we need to maintain is causality, so the partial ordering, increasing sequence number for a single actor. And the last part of this pipeline would be the materialized views that we had previously. So the first one is exactly the same. It's events by persistence ID, but the second one is events by tag. Previously, we had to use the time bucket, but now we have much more control. We can replay the previous stream as many times as we want. We can maintain any state as we want. So we can just build very efficient view, and we can maintain the subpartitioning as we want. Similarly, all persistence IDs, previously we had to maintain the set of all persistence IDs that we have already emitted. But now we can create a very efficient view and query that very, very efficiently. The only thing that we, again, need to maintain is the causal consistency in all these views. So the pipeline not only makes us independent on Cassandra 3, but it also gives us all the guarantees that we needed, such as the causality, consistency, and performance when reading from the database. But most importantly, it makes us the reasoning about consistency and failures in this pipeline very, very efficient and simple. So you might be thinking, why wouldn't we, when an actor writes an event, why wouldn't we immediately write it into all these views? Why do we have to go through that long pipeline? So the reason is we're in distributed environment. So we cannot just simply write in a single transaction. We could do that in a relational database, and that would work very well. But in distributed environment, we would have to do a distributed transaction, which is very expensive. Cassandra batches, so we created one batch. Cassandra batches only give us atomicity, but not isolation. So the batch will always succeed or fail, but it only has eventual consistency, which is a big issue for us because the events by persistence ID that is used for replay needs stronger form of consistency. It needs read your own writes consistency. Otherwise, an actor could write events, then fail, and it would recover, and it would not read all the events that it has written. It will only read part of them, which is a big issue because you definitely need consistency for your actors when recovering from a failure. Okay, so we could write into a single partition the events by persistence ID because that's atomic and isolated. So we would have the guarantees that we need. And then we could write a different batch with all the other views because they don't have that need of read your own writes consistency. The problem with that is this is called dual writes. So you do two writes, but the system can fail asynchronously at any time. So it can happen that it fails and one of the writes succeeds, but the other one doesn't. And therefore, we would have inconsistent data, which is something that we, again, cannot afford. All right, so let's discuss some of the concepts that we use in this pipeline. First one is event time processing. Most stream processing systems only use processing time processing, which means they process the events as they arrive. But very often, in many business use cases, you want to use the event time. Event time is the time the event was created, or some business time associated with that event. And those two times are not the same because the pipeline can cause a delay, or the network transitioning. So these blue events were created at around the same time. So they belong together. We would want them to be in a window together. But one of them was delayed. So if we used processing time windowing, when the blue window closes, this one event would not be there, would not be in the window. So we really want to use event time windowing. So we need to wait for a period of time and until all the blue events are in the blue window and then close the blue window. There are two difficulties usually associated with that. The first one, we need to keep a buffer. We need to keep a buffer of the blue events because we did not close the window. And the biggest difficulty is we need to maintain correctness, the completeness. which is difficult because we don't really know how many blue events there are. We don't know how long we should wait. We have only this one, but there could be others more delayed. So we don't really know how long we should wait. This is usually handled by using watermarks, triggers, or some sort of heuristics. Another concept common in distributed environment is ordering. Often we don't have access to a global shared clock that would be atomic and accessible by everyone. And also, often we don't have communication patterns available to be able to use logical clock or vector clock. So many stream processing systems, when reading from a database, they actually only use a single thread and a connector like JDBC, and they query the database and create a single order of operations, which can be quite inefficient. The other option is to use what Spark Cassandra connector, for example, uses, because partitions in Cassandra are independent, so it can query them heavily in parallel and produce multiple independent streams. So the way this applies to our use case is that we have these multiple physical streams, these write-ahead logs, but we need to merge them into a single stream where we define the order of events. We can merge this one, so event 0 for ID 0, but because we're merging in parallel, we cannot merge this one because it is event 2 and we're expecting event 1. So what we need to do is to maintain some sort of buffer of the last merged ID for the particular persistence ID, and we just progress this buffer and this pointer until all the events are merged. And therefore, we maintain the causal consistency, the stronger form of consistency that we needed, which is very similar to event time processing that we talked about before. Similarly, I talked about ordering, because we have this partial order per persistence ID, but other events for multiple actors, they don't have any relationship at all. They don't have any order. But we write them into the write-ahead log immediately as we can, and we write them at around the events that are written at around the same wall clock time will be merged into the final stream at around the same wall clock time. It may not be exactly the right global wall clock time, but it will be pretty much very close. And if there are any inconsistencies, it doesn't matter that much because there's no ordering defined, so we can just create our own. Another concept that I need to talk about is replay in this case. Because CQRS or similar pipelines only give us eventual consistency, we cannot just replay the events that are in the materialized view. Because there might be still some events for the same actor in the processing pipeline, and therefore we wouldn't have the read your own write consistency that we absolutely require. So we need to finish the replay, by actually replaying the elements that were not yet merged into the materialized views, and as well complete the reading by replaying those that are still in the write-ahead logs, which may not seem efficient, but there are many frameworks that actually do this, such as Eventuate. Another concept in distributed environment is exactly once delivery. So we would want to send messages across network to another machine, so the publisher to the subscriber, but the network is unreliable. It can lose messages, it can reorder messages. Similarly, so most stream processing frameworks send some sort of acknowledgements. Storm, for example, sends acknowledgement for each element. Others send acknowledgement for batches of elements for efficiency, but the acknowledgement may be lost as well. And similarly, even the machine, so both the publisher and subscriber can die for unbounded amount of time. So how do we achieve exactly once delivery, reliable delivery of messages between the publisher and subscriber? Usually, we need some sort of durability on both ends of the pipeline. So we need durability in the publisher, so it can replay the messages many times, and we need reliability in the subscriber, so it can deduplicate messages if it receives the same message multiple times. How this is usually handled in stream processing frameworks is they either duplicate the processing pipeline, so they have multiple replicas, and if one of them dies, the other one can continue processing, or they write the data they receive immediately into a write-ahead log. So it becomes a replayable source, and therefore they can reliably retransmit it multiple times. This is Apache Flink, an example. It uses a distributed snapshotting algorithm, and it assumes replayable sources. So it snapshots the current progress of the replayable source, and it also snapshots the current state of all stateful operations. And then if there's a failure, it will just recover from this snapshot and replay the sources from the last known point in time. This is how this thing is implemented in Apache Gear Pump and other stream processing framework. The API just gives you the last known global time of the last processed event. And if there's a failure, we can just recover from that failure by replaying the source from the last known event. Similarly, this is Apache Spark Kafka connector, and similarly, when it fails, it just reads the last known offset for Kafka, and it replays the events from that point in time. In our case, in our alternative architecture, this is actually even simpler, because we can just simply selectively progress an offset when merging the streams or when working with the streams. And if there's a failure, we can simply have durably stored the offset and recover from that failure. Or we don't even need to do that, because if you think about it, we already have durability on both sides of the pipeline. So we have the write-ahead logs, and we have on the other side, we have the materialized views. So if there's a failure, we can potentially just compute the offset progress from these durably stored databases. Another concept commonly known and commonly used in distributed environment are optimizations. We don't need to only optimize on a single machine as we normally would when using monolithic applications, but we also need to optimize the distributed environment. Such as simplifying the computational graph, reducing communication, pushing operations to database, optimizing partitioning, improving locality of the data, scaling dynamically based on load, or placing operations on the nodes where they will have the best performance. So some operations need more I/O or memory or CPU, GPU, so we can place that operation on the node that actually can do that well. In this example, we query a database, then we do some projection, filtering, and then finally we do some group by. So we group events that have the same color to the same physical node. But potentially we can push some of these operations to a database. So the database can do select where, therefore we get rid of some of the processing stages. And finally, we can even push the group by to the database. That's not always possible. Not all databases, especially distributed databases, can do group by. But if we know how the data are partitioned, how they physically live on the machine, we can potentially achieve that. This is an example of Spark Cassandra connector. So Spark knows or asks Cassandra what partitioner it uses, and it can then knows how the data are partitioned in the cluster. It knows which node has which token range. So it can actually use that knowledge to construct a query and query the data directly from the database. Spark also knows where its nodes live physically, and it knows where Cassandra's node live. So it can potentially, if Cassandra and Spark nodes live on the same physical machine, that Spark node can query the same Cassandra node on the same physical machine, and therefore it will be more efficient, and it will just optimize some of the querying across or moving data across network. This is another example from Apache Spark. This is from the Catalyst optimizer. So it optimizes the computational graph. This pushes filters through projections, so it simplifies the graph and becomes more efficient. It's not Spark specific. Apache Flink, Google's TensorFlow, and other frameworks do exactly the same thing. You might have noticed I was talking a lot about streams, but they were actually represented as database tables. The reason is there's a lot of relationship between database tables and streams. A good example is the log. So log can be turned into a stream very easily. A mutable table is a snapshot of a stream, and changes to a mutable table are a change log, which can again be represented as a stream. But we don't have to demonstrate that on a stream processing system. We can use simply Akka. So again, we have Akka cluster or Akka sharding, so multiple actors living on multiple physical machines. And each actor can be addressed by a key, by its name. This actor receives messages, it does some transformations to its internal state, and produces messages. Both these can be seen as a stream. And the actor has a mutable state. This mutable state, if you think about it, it's essentially just a key value store. It can be addressed by this actor's key by its name, and you can access it as a key value store, which is localized to a single thread, so you get consistency for free. And it's also how many stream processing systems actually handle a state partitioned by key. But this state is unreliable. So we can, however, use this write-ahead log, akka persistence, to reliably store the changes to the mutable state, and we can recover from failures. And as you've seen, this database table, this write-ahead log, can again be turned into a stream quite easily by using Akka Persistence Query. Actor can also store a snapshot, so it does not have then to replay all the messages in the log, but it uses this snapshot and then replays all messages that happened after the snapshot, which we have also discussed previously in the change data capture. And actors or Akka can also have a distributed state, a global state, which can either be an event bus, event bus, or CRDTs, or a distributed snapshot, which again can be represented as both a table or a stream. As Martin Kleppmann and others correctly point out, there are many use cases for infinite streams of data. So assume we have this original system. It can be a database table or any system. And if it emits a stream of all events or of all changes to its state, anyone else can then subscribe to this stream, and they can be updated all the time. They don't have to query for the data. They don't have to send a request. They will always be kept updated with the latest changes to its state. This is very useful. We can reconstruct the original table in a different way, such as a cache or a search index or a materialized view. Or we can just consume it in any microservice or any system and be kept up to date all the time. This is used, for example, in so-called streaming data pipeline, where we have something like Kafka in the middle, something that can handle large-scale streams. The streams then can be queried, they can be replayed, and anyone who's interested can publish their data into this streaming data platform. So any social media devices, any services or microservices can just publish the stream of events into this streaming data pipeline. And then anyone on the other side who's interested in the data can query or be updated, can subscribe to the stream and be updated all the time immediately without having to query for the data. So we can have, again, something like search engines, applications, services, anyone who's interested. We just need some common interface, such as serialization format that can handle versioning. But then the teams can work completely independently on each other, and it gives us all the guarantees that we discussed previously. So it gives us the consistency guarantees that we need exactly once delivery, fault tolerance, because these are all distributed systems. We can use things like load balancing, so create multiple replicas of the same service, and all these things can be achieved if we use or if we build the guarantees that we discussed previously. This will work very, very efficiently. But the most common use case of streams are just general distributed systems. So we have multiple microservices. Each microservice has its own database, depending on what consistency it needs. So it can use an SQL database, no SQL database, or CQRS. And the services communicate with each other by sending messages. They don't do a request response. They just send message whenever needed, and they will receive message, and they should be able to handle that message at any time in the future. And again, if we achieve the same guarantees that we discussed in the stream processing pipeline, such as consistency, exactly once delivery, durability, fault tolerance, and all these, then we can have a very reliable and very efficient distributed system or general microservice architecture. So you might have noticed this was not really the most common example of a distributed system or microservice architecture, because it wasn't. It was a very specific one. It was an example of Google's TensorFlow using building asynchronous data and model parallelism for machine learning model training. If you're not familiar with TensorFlow, it's Google's framework for large-scale machine learning or large-scale data processing. It works in distributed environments, so it can have multiple machines. Each machine can have multiple devices. Device is a CPU or a GPU. And then Google TensorFlow describes the computation as a computational graph, a directed acyclic graph. And then each node of that graph is assigned to one of the devices. They sometimes have different requirements than microservice architectures, such as they have reduced sometimes consistency requirements because many of the machine learning algorithms can handle randomness or noise quite efficiently. Sometimes they don't want to process each message individually because they build a batch, because they can use BLAS or a GPU computation on that batch. But other than that, they have exactly the same guarantees. So they need to be able to send messages to each other across network. So they need the reliable delivery. They need exactly once delivery. And they need fault tolerance because each of these machines can die at any time. They definitely need optimizations because this process is run many, many times in many iterations. To be efficient, it needs to be very, very well optimized. So it has exactly the same guarantees. They're not using Akka or any other asynchronous messaging system. They're using their own technologies like Google gRPC, but the concepts are exactly the same. So this may all look really appealing, really interesting, but there are still some challenges that have to be solved when we're building such system, especially in distributed environment, such as exactly once delivery, consistency, availability, fault tolerance, cross-service invariance, therefore distributed transactions, automated deployment and configuration management, automated elasticity, so the ability to scale up and down and handle failures without downtime, upgrades of versions of our services with no downtime ideally, graceful shutdown of services, so not losing data or messages when shutting down a service. Distributed system verification, logging, and traceability is very important and is not usually granted, or split brain scenarios. All these are often taken as granted, as solved problems, but you really should focus on these and verify that all these are correct, especially in distributed environment. So in conclusion, we moved from request and response, mutable state, and synchronous messaging, request-response type of messaging to streams, asynchronous messaging, and most importantly, we have to treat distributed systems as production ready. We need to verify them, and we definitely need to treat distributed systems as first-class citizens. Thank you very much. Any questions? So the question was whether we can write into Cassandra and Kafka at the same time when, for example, in Akka Persistence. Unfortunately, no, not at the moment. And you still couldn't write into both because you would have the dual write scenario. So the only way is to write it consistently with strong consistency into one of these, and then read it from there and continue the pipeline similarly to what we have seen. Okay, thank you very much.